Okay then, so this time I want to talk about conics. This is one of my favourite aspects of projective geometry because here we really get to see a lot of the devices and things which we've learned about throw loads of light upon the fantastic field of the study of conic sections. Conic sections have been studied since ancient Greece. Apollonius was one of the most distinctive geometers, and some of the notions about combining polarity with conics came about from him. However, they were understood in much deeper levels by the German geometer Van Stout, and today we're going to find out how that worked. So, the thing to bear to mind is that normally, like in the historical run of things, people started out figuring about conics and they thought of conics as rigid forms in the context of Euclidean geometry. However, in projective geometry, we define what conic is abstractly, and we find that all of the well-known conics in physical space, like the parabolas and hyperbolas and ellipses and so forth, really in some sense are all kind of projectively equivalent to each other. They look sort of the same in the projective plane because we're not giving any of their infinite lines or points any special treatment. So this is already quite an interesting feeling. But what I think is a lot more exciting is to be able to describe these conics generally in terms of these ideas about polarities. So, polarities, just to remind you, unless you've forgotten, polarity is a projective correlation of period 2. And so some polarities have no self-conjugate points. Again, if this terminology is lost on you, I recommend you watch the first 10 minutes of the last video I recorded. Anyway, okay, so polarities can come in one of two kinds. We can have so-called elliptic polarities, which don't have any self-conjugate points, and we can also have so-called hyperbolic polarities, which have at least one self-conjugate point. So we've seen this kind of thing happen again and again. We saw it happen for one-dimensional projections. People like to count how many of certain types of points they have and use these notions to define things as either hyperbolic or elliptic or whatever. But although we are going to get talking on to conics quite soon, it's worth bearing in mind that these particular names are not especially related to conics in the physical sense we normally think of them. Because actually, it's only these hyperbolic types of polarities which truly have the kind of structure we need to be able to induce conics. Okay, so I want to give you a little sort of preview of what's coming up. So we're going to look at hyperbolic polarities. We're going to see that they induce something called a conic. Actually, the way they induce it is that the conic is just the set of all self-conjugate points under that special kind of polarity. Now, when we get these conics, what do we do with them? Well, we play with them a lot and we think about the kind of polar relationships between them. because essentially we're really interested in the polarities. But the thing is that when we've got these hyperbolic polarities, they essentially create conics. And we can really think of the whole idea of doing things to do with polarities completely in terms of the shape of a polarity itself. For example, the shape of the conic itself. So, for example, if we have a hyperbolic polarity and it makes a conic which is a circle, well then essentially we can think of things like finding the polar of a point using the circle. We no longer talk about using the polarities, that goes to the background, and we stick with the physical kind of ideas of basically using conics to find the polars or the poles of different objects. And it all works out quite nicely. But I just thought I'd give you a little motivation of this before we get too throng with extra work. So this here is a circle and you have a green point. Now, as I've said, there'll be a polarity related to this circle. And my question to you is, how do you find the polar of this green point? And I don't expect you to know the answer, so it's illustrated by this diagram. The polar is the thing that you get by drawing tangents to the circle and then drawing this green line through those two tangent points. That gets you the polar of your line. This is quite a profound idea because by keeping using this method, every point outside the circle can be associated with a line inside the circle. But there's more. Now here's a proper question for you. The answer will become apparent during the course of this lecture, so you might want to pause the video and think about it if you want to have a crack. Basically, I'd like you to see if you can draw a line outside of the circle and see if you can determine that line's polar. So draw another red line that doesn't touch the circle at all. And now see if you can work out what the pole is of that red line. And I'll give you a clue. Draw a couple of points on the line and work out where their poles are. Good luck. Okay, so later on, these ideas about having to work out where polars are going to become a lot easier when we encounter various theorems. But this particular configuration here is something set up quite near the introduction of Coexeter's introduction to projective geometry. And well, I think it's a little bit, some of these things here are going to get proved later, so you're sort of going to have to take my word upon it. So basically they're talking about hyperbolic polarities. They are the polarities which make conics, so that's nice. And they're saying that each harmonic each harmonic polarity has a conjugate line, and it can be written in this standard form that we were discussing last time, which is where we have a self-polar triangle with vertices A, B and C, and the poles of those vertices are the opposite sides of those vertices. And we also have a couple of other points, capital P and lowercase p. And in this extreme example, this capital P is actually a self-conjugate point. So in other words, capital P lies upon its line, which is the polar of P. So it's just sort of taken for granted here that we have such a hyperbolic polarity of this form. But we can then use it to learn things. And later on we will see that it's possible to make hyperbolic polarities of this form from conics. So later on we can suspend our disbelief, as it were. But if you just have a look at the top diagram, you can see a little bit about what's going on. We have a self-polar triangle. It has green, blue and purple vertices, and opposite each of those vertices is an opposite edge of the same colour, which also turns out to be the pole of that edge. Now I've done this kind of polarity with respect to the circle, which you can see drawn here too. Now, not only claiming that the self-polar triangles all exist when we have these conics to play with, or when we have hyperbolic polarities, which they do, we're also sort of assuming that there's going to be an extra sort of self-conjugate point. That doesn't seem too unreasonable, because our hyperbolic polarities are really defined as having these points. Anyway, hopefully the kind of holes in this setup will be filled as we talk about later results. Okay, so let's get back to the important things. Hyperbolic polarities are the things which give rise to our conics, because the conics are a set of self-conjugate points of those hyperbolic polarities. So we know that hyperbolic polarities have at least one self-conjugate point, but if the conic is just the thing you get by joining all the self-conjugate points, then, well, we better have plenty of them to make a conic. So that beckons the question, how many of these self-conjugate points do we really have? Do we have many? Well, there's a claim here, a theorem really, I suppose, and essentially it does infer that there are going to be lots and lots of these self-conjugate points. So if you look at the above diagram, we have this point P, which is a self-conjugate point, and we have another line through that point P. Now the claim is that that line, or in fact any line through P, which doesn't go through its polar, little p, must have another self-conjugate point on it. And if we can claim that, obviously that infers the existence of many, many other self-conjugate points. But how do we prove it? Okay then, so firstly, the result from the last lecture, I think it's the first result, FPG 10a, well, that stated that any self-conjugate line can only have at most one self-conjugate point on it. And so, and P is a self-conjugate line, so big P can only be the only self-conjugate point on it. Now, another one of these results from the last lecture, Theorem C, states that if we look for any line through capital C, but doesn't pass through its polar, or doesn't touch its polar, little c, well, it doesn't, it's not the same line anyway. So any line through big C that's not the same as little c, that's going to have an involution of its conjugate points. We've seen this phenomenon before. This is where you've got a line and doing some kind of polarity on it, and it's not fixed, and then you end up with, for example, a point X getting sent to a polar X, which also intersects the line, and which intersects it to make the sort of polar of point X, Y, appear. And it turns out that these polars of one another are basically swapped around by involutions. So we get these involutions occurring as a consequence of the polarities. Now, as we've already said, P is an invariant point on this line. However, there's a theorem, and that says that if you've got a couple of invariant points and you have an involution working upon a line, then one of those invariant points is going to be the harmonic of the other invariant point with respect to a couple of other corresponding points on that line. So what that essentially means now is that that second line which we chose, which is drawn in grey on the diagram, is yet another point which has, well, under the involution an invariant point, but the big picture is that under the hyperbolic polarity, that new point on that grey line is a self-conjugate point. So that pretty much proves our theorem, because we've proved that for every line, as in the grey line, through this point, this self-conjugate point, there's going to be another self-conjugate point. So this establishes the multitude of the self-conjugate points in this system. It's important to remember how we define terms like secants, interior points, exterior points, tangents, etc. for conics in projective geometry, because sometimes there's going to be things about these objects which are true in certain kinds of projective geometries but false in the standard Euclidean geometry. So firstly then, our most basic thing behind the conic is a polarity. And a polarity is either hyperbolic if it has at least one self-conjugate point, or it's elliptic if it has no self-conjugate points. Recall that a polarity is just a period 2 projective correlation of the projective plane. So it's sending points to lines and lines to points bijectively whilst preserving incidence and non-incidence. And it has period 2. Okay, so we have this conic then, and the set of all points belonging to the conic, we'll often just call that the conic. That's the set of all self-conjugate points. So we have this result which basically says that when we have a hyperbolic polarity, the conic which it defines, as in the set of self-conjugate points which it defines, will have many different points in it. So the kind of dual to these points which essentially form the conic are the lines which are tangential to the conic. So because in projective geometry lines and points essentially have the same kind of footing as each other, We can equally think of a conic as being generated by a kind of envelope of tangential lines. So, in the sense of Euclidean geometry, the most familiar conic to you will probably be the circle. And then we have the ellipses, the hyperbola, and the parabola curves. But really, in projective geometry, we think of all of these as being on the same footing. And typically, we take a kind of point-wise approach. And when we use the term conic in projective geometry, we're referring to the set of self-conjugate points under the polarity, the hyperbolic polarity, which defines the thing. And so, a kind of basic way, if we're working with a circle, a basic way to calculate the polar of a point outside of a circle is if you just, this is all in the Euclidean sense, I'll give a wider definition of this later, but just working in the Euclidean sense, if you want to work out what the polar is of a point exterior to the circle, just draw the two tangents from that point to the circle, find where those two tangent lines kiss the circle, and draw the line which connects those two places where those tangent lines meet the circle. And that new line, that will be the polar of the initial point. So this gives us a definition of the polar of an exterior point, but we can actually go further using some other methods and define the polars of interior points as well. And also we can do this for more general types of conics. So okay, let's introduce some proper terminology then. A secant is a line which goes through two self-conjugate points. In other words, it's a line which goes through two of the points of the conic. So, for example, if you draw a line through a circle which goes through the circle at 2 points, that would be a secant of the circle. The kind of opposite idea then, the opposite type of line, is what's called a non-secant. That's a line which doesn't go through any of the points of the conic. So in the sense of a circle, it's just a line which misses the thing entirely, doesn't touch it at all. And then the kind of intermediate case is a line called a tangent. A tangent to a conic is a line which just goes through one point of the conic. So we use these notions of secants, non-secants, and tangents to define whether points are exterior or interior. And I think one needs to be a bit careful here to remember the definition, because the ideas of inside and outside are quite easy to confuse in some cases on the projective plane. We define an exterior point with respect to a conic to be a point which has two tangents going through it. And the opposite idea then is an interior point. An interior point is a point which has no tangents going through it. So a tangent, as I just said, is a line which has one self-conjugate point, one member of the conic in its range. So you can see that there won't be any points which have more than two distinct tangents going through them, because a tangent is a line touching a self-conjugate point, and the kind of dual of that idea would be a point which has a self-conjugate line through it. And that's precisely the same thing as a point on the actual conic on the kind of boundary, the intermediate place between the interior and the exterior. So the idea of an exterior point, that's a point which has two tangent lines through it. Well, the dual of that idea, instead of being a point with two self-conjugate lines through it, the dual idea would be a line with two self-conjugate points on it. And that's exactly what a secant is. So the notion of a secant is the dual of the notion of an exterior point. The notion of a non-secant line is the dual of the notion of an interior point, and the notion of a tangential line is the dual of the notion of a point actually on the conic itself. So it turns out to be quite useful to relate these notions back to those of involutions, as we discussed before when we were talking about polarities in general. Okay, so it turns out to be fairly useful to relate these ideas about polarities to involutions. Let's imagine we have some secant, let's say lowercase x, and so that's going to be a line which goes through 2 points of our conic, and let's say that under our polarity, which we can think of as a mapping f, this secant line little x gets sent to a point capital A. So we can think of all of the points on this secant line little x, and we can imagine a point on this line, let's say capital A. So capital A is a member of the range of little x, and under our polarity, this point capital A is going to get sent to a line. And we can consider the place where this line, which we can call f of A, because we're applying the polarity f to the point A, we get a line f of A. We can consider the point f of A meets little x. That's the place where the image of this point A intersects with our line. We can do a similar thing for every member of the range of this line x. And essentially we can then visualize the thing as a mapping from the range of x to the range of x. So we think of it as a mapping, I've written it as J here, which sends a point capital A to the point f of A meets little x. So that's going to be an involution of this secant line, of the range of this secant line, and as we discussed before, and also note that it's going to actually be a hyperbolic involution. Why? Well, because it has two invariant points, the points where this secant line little x intersects with the actual conic. They're going to remain stationary under this transformation. So when our line is a secant, the sort of involution induced upon it is going to be hyperbolic. Similarly, the involution induced on non-secant lines is going to be an elliptic involution, because it won't have any invariant points, because such a line will never cross the conic. Okay, so that's the idea with respect to secants and non-secants. We can also consider the dual idea of how involutions are related to interior points and exterior points. So now rather than being mappings from ranges of points to ranges of points, now we're going to think about involutions which send pencils, as in sets of lines through a point, to pencils. So in particular, let's think about an exterior point, capital Y. So let's think about the pencil of lines which go through this point, capital Y. Well, since it's an exterior point, by definition, it has to have exactly two lines through it, which are tangent lines, self-conjugate lines. Now, the effect of our polarity is going to be to send every line, little y, through this point, big Y, to some point. So every member of the pencil gets sent to some point. And the point which something gets sent to can be associated with another line through big Y. If we have a line little y through this point big Y, let's say that that line little y gets sent to some image f of y. Well, f of y is going to be a point, but if we then consider the line which joins big Y to f of y, well, that's just going to be another line through big Y, just another member of the pencil of big Y. So this is a kind of dual notion to the thing we were just talking about with respect to ranges. And essentially what we're doing here is thinking about or sort of representing how this polarity acts upon the pencil of Y by thinking of it as an involution of the pencil of this point Y. So under this involution, the line little y gets sent to the line joining big Y to the image of little y. So under this kind of involution, the tangent lines are going to be the fixed points, the invariant elements, not points, I shouldn't say points. The tangents are going to be the invariant elements, the members of the pencil which are left unchanged. And so it follows that if we have an exterior point and we consider such an involution on its pencil, that involution is going to have two invariant elements. So it'll be a hyperbolic involution. That's for an exterior point. And if we consider an interior point, it won't have any tangent, so it won't have any invariant elements under the involution. Okay, so there's a fairly rich theory behind all this stuff. For example, hopefully you can convince yourself that every exterior point is going to be the pole of a secant, and every interior point is going to be the pole of a non-secant line. Also, if we have a line little x, which is a tangent line, then it turns out that every point upon x, which doesn't belong to a conic, has got to be an exterior point. Perhaps you can find a proof of this for yourself. So then it follows that if we just take a couple of tangent lines, distinct tangent lines, x and y, and we find their meeting point, well, that's got to be an exterior point. And by duality, that's going to be the point little x meets little y. Well, that's got to be the pole of the line through big X and big Y, where big X and big Y are the poles of lines little x and little y. Well, since little x and little y are tangents, big X and big Y have to be members of the conic itself. So that means that this line between capital X and joining capital X and capital Y, that actually has to be a secant. So in other words, the dual of the meter of two tangents is a secant line. Okay? And as I was saying before, it's important to be clear about these definitions, because you can encounter some rather interesting and peculiar examples if you pick the right kind of projective spaces. For example, there are cases where you can have lines through interior points which are not secants. I'll leave it up to you to see if you can cook up an example of something like that which satisfies the axioms of projective geometry discussed earlier on. However, a lot of familiar ideas about conics and things do follow quite naturally. So let's consider the problem of finding a secant for a given point. So let's say we have this point capital X and we want to find a secant through it. Well, if it's an interior point, then all we have to do to get a secant is just draw any line we like through this point X. And such a line, well, since we have an interior point, by definition, every line through this point is not a tangent. And so let's say we join this point capital X to some point capital Y on the conic. Well, we know that this line XY isn't a tangent line, and we know that it holds some points of the conic, so we know it has to be a secant. So it's fairly trivial to find the secant of an interior point. If we have a point that's actually on the conic, capital X, which is on the conic, then what we can do to find a secant of it is just pick another point Y, which is distinct and also upon the conic, and then the line XY again has to be a secant line, because such a line holds 2 points from the conic. Now, the most interesting case, I think, is if we have an exterior point. So perhaps you'd like to pause the video and see if you can come up with a sort of foolproof method of finding a secant through an exterior point. Okay, so I'll tell you how one way to do it. If we get such an exterior point, capital X, and then we pick 3 distinct points, A, B, and C, on the conic, then we can consider these 3 lines, AX, BX, and CX. And the claim is that at least one of these 3 lines actually has to be a secant line. Now, the reason is that since X is an exterior point, it has 2 tangent lines meeting it. But we've just described 3 lines which meet it. So at most 2 of these lines can be tangents. So one of them must be a non-tangent line, and it can't be a non-secant line either, because, as I've just said, it contains a point of the conic, so it has to be a secant line. So either AX, BX, or CX has to be a secant line. So we've just talked about quite a lot of different facts about these conics. Going back just briefly to the idea of involutions, it's useful to think about if we have a secant which goes through conic points X and Y, well, we can write the involution of that secant using our standard kind of bracket notation, because that involution has 2 pairs. One pair is X, X, and the other pair is Y, Y. Those are the 2 invariant points under the involution. And recall that we need to specify 2 pairs of mates to completely define an involution. So okay, now I'm just going to list off a load of theorems about conics. The first few of which can be proved using the ideas which I've just discussed fairly, well, relatively easily. Some of these other ones do have more involved proofs, and perhaps in a later lecture I shall go through the theory of this in more detail. So, firstly, we've already pretty much established that if we have, let's say we have a secant, and I'll write that secant as capital X, capital Y. So that's a line going through points, conic points, big X and big Y. Well, in that case, if we think about the involution that works on that secant, if we think about the polarity, we're thinking about the big picture now. So we think about the polarity working on that secant. Well, it turns out that a couple of points on that secant will be conjugate to one another. Precisely when they are actually harmonic conjugates to one another with respect to these points big X and big Y, where this secant line actually intersects with the conic. So Theorem A establishes that points which are conjugate on a secant are going to be harmonic conjugates with respect to the intersection points of the secant. And Theorem B establishes that harmonic conjugate points are going to be conjugate points with respect to the polarity. So another very useful result is relating quadrangles to the idea of self-polar triangles. So recall that earlier on I was talking about how any of these so-called hyperbolic polarities can be expressed using this notation A, B, C, capital P, lowercase p, which is basically an expression of the polarity in terms of a self-polar triangle. And basically this next result gives us a method to find such a self-polar triangle, because what it says is that if we just get one of these conics and just say draw 4 random points on it to form a quadrangle, okay, we have the stipulation that all these points have to be distinct and no 3 of them can be collinear, but that's usually fairly easy to satisfy. And once we've done such a thing, we then just create this complete quadrangle by drawing all the possible lines between these 4 points which lie upon the conic. And if we have a look at the diagonal triangle of such a quadrangle, well, that's actually going to be a self-polar triangle. So, in other words, take a conic, pick 4 points on the conic, say randomly, and almost certainly, if you draw all the 6 possible lines between the points, and then you find the 3 new points that get generated, those 3 new points, the 3 points of the newly generated diagonal triangle, they're going to form a self-polar triangle, which has this nice property that each of its vertices gets mapped to the side opposite it under the polarity. Okay, and sort of a useful, closely related result to this, probably the most useful result actually, in some sense, that we're going to talk about in this lecture, allows us to actually find the polar of any given point. So let's say we have a point capital X, and we want to construct its polar. Now, I've already told you how to do this if we have this special case where capital X is, say, an exterior point of a circle. But what about more generally? What about maybe if X is an interior point, or we have, we could have all different kinds of conics. I mean, I'm always using circles in these drawings, but all of these facts hold equally well for parabola or whatever, or hyperbola. Anyway, so say we have this point capital X, and it's a point which, I mean, if it's a point actually on the conic, on the boundary, then its polar is just going to be the tangent line to that conic, which meets that point. But let's say it's not a point which is actually on the conic. Let's say it's either an interior or an exterior point. How do we find its polar? Well, here's one way. Well, what we can do is, if we draw a secant through this point capital X, let's say that secant meets the conic at 2 points, A and B. Now let's draw another distinct secant through X. Let's say that one meets the conic at 2 other points, C and D. So now we've got these 4 distinct conic points, A, B, C, and D. Now, it turns out that if we then find the meeting point of the lines BC and AD, well, that'll give us 1 point of this kind of generated diagonal triangle. And another point of it will be where the line AC meets the line BD. And if we join those 2 points, well, the line little x joining them, that's actually going to be the polar of capital X. So this is a fairly remarkable result because it doesn't actually matter really how you choose these 2 lines AB, these 2 secants AB and CD, just as long as they're distinct and they have distinct intersection points with the conic. So just to summarize them, we have the BC.AD joined with AC.BD is going to be the polar of a point X where AB and CD are 2 secants through this point X. So this is a very nice result which allows us to construct polars in general. And if we instead want to, let's say, want to find the pole of a line, well, we can do that fairly easily using duality. So if we just pick a couple of points on that line and work, say, A and B, and work out where the polars of A and B are, then the intersection point of those polars is going to be the pole of that line. Okay? Okay, so that's a bit about how to find out about how to construct polars and poles. What about if we want to find the tangent? Let's say we have a point X, big X, which is actually on a conic, and we want to find a tangent to that point. How do we do it? Well, what we can do is if we just take any secant, little y, that goes through this point, big X. So let's let big Y be the pole of little y. So then it turns out that the line through big X and big Y is actually going to be a tangent to the conic, which goes through this point big X. I'll leave it to you to think about that one. Okay, so we're nearing an end now of this lecture, so I'm just going to talk about a couple of famous results. One of which, if I can pronounce the name of the author, Seidewitz's theorem. Okay, Seidewitz's theorem. So this is a fairly famous result concerning conics in the projective plane. It says that if we have a triangle which is inscribed upon a conic, and we've got a line which is conjugate to one of the sides of this triangle, well then, if we look at where such a line meets or intersects with the other two sides of the triangle, well, it'll do that in two separate points, and Seidewitz's theorem claims that those 2 points are actually going to be conjugate to one another. So in other words, any line conjugate to one side of a triangle is going to meet the other two sides of the triangle at conjugate points. So there are many other remarkable results about conics which I think are well worth taking a look at. For example, Steiner's theorem is a really fundamental result about conics. There are several different ways to relate this idea. One of my favourites is that if you have a projectivity from one line to another, and it's not a perspectivity, then if you look at the set of all lines joining a point to its image under this projection, this projectivity, well, that'll form the envelope of a non-degenerate conic. So this gives us another way to think about conics, and an interesting idea about how these curved forms can appear from the sort of linear ideas of doing projections. So in fact, one can define conics in terms of Steiner's ideas. Other really remarkable results are Pascal's hexagon theorem and its dual Brachion's theorem, and also the closely related idea about how 5 points define a conic. So I've already done videos touching upon these topics, so I shall put some links in the comments section, and I strongly urge anyone interested to check out the really remarkable theory of conics, which this lecture is only really scratching the surface of. So thank you very much for your attention. I hope you've enjoyed learning about the foundations of projective geometry.